Levi,
Yes.
do you see the content of our screen?
Yes.
You do?
I do.
Excellent. I was not. Ah, John, happy to see you. Hi, John. Do you hear?
I don't see John.
I do
Oh, he's
see.
at the bottom.
Yes, but he's probably not hearing us.
Oh, here he is.
Ah, here. Super. It is better arrangement than in a classroom. John, do you hear us?
Yeah, I can hear you.
Okay, excellent.
Once we got new speakers too. Hear the bass.
Yes,
voice.
yes, it becomes much better than it was before. Did they make this touch screen? Not yet. Okay, so they still have a improvement direction to make it touch screen. Then it will be really perfect. Well, many thanks for coming and for investing your time. This today we are here for just for the testing equipment and informally chatting, but starting from next Tuesday it will be regular meetings together with Dr. Kidener's group, because substantial part of her group is in Los Alamos, and there is not efficient to do small meetings, while merging can be more efficient and provide more feedback. We will need to develop a schedule that matches interests of both groups, but both groups attend Sanibel, and most of this semester will be invested into preparing for Sanibel. I will give a quick update of our group, what we were doing and what we plan to do. I don't know if the second leader will decide to do the same for her part, but then we need to set up a schedule of presentations, or at least to update them for each next couple of meetings. I suggest that we keep the Google Docs thing, share the link so that everyone can edit, and remove his or her name from speakers if he or she doesn't like it, and update if volunteering, so make it a self-growing collective editing document. And plans are to, as usual, preparation to Sanibel presentations and papers is the priority number one. Research update in a little longer form is priority number two. The reading journal club is priority number three, and the fourth priority, the knowledge transfer, probably will not be implemented this semester. We did enough last time. So what is going on? So it is a little update. I was hoping a lot that any of undergraduates will come, because for the rest of us it is not a new information. So it is quick survey of what is going on in the group. So basically we are working in two directions that could be complementary to each other, but they are rather independent. So expert in one direction can, it's different expertise and different areas of knowledge. So one direction is photophysics and another is photochemistry. So photochemistry is how bonds are broken or formed upon heating or irradiation, and photophysics how electrons are transferred. In the ideal world, we would combine this and have a super piece of software that does everything at once, but it is not efficient from computational cost point of view. Levi may object and tell that there are some pieces of software that do electronic and nuclear degrees of freedom propagation at the same time, and he was exposed to running these codes. But such codes that are universal, they are limited by this number of atoms in the systems that they process. So here we are trying to be a little more realistic and work with mid-sized systems. So what is on the screen is what has been done in the last year or half year, and it is a result of effort and research activity exposed to group meetings like this one. So most of these publications resulted from collective discussions on the group meeting, and were, although each project had a primary author, the activity of getting together and providing feedback is a critical key to success. So those are photochemistry works. So the semi-review or detailed overview of methodology by Dr. Han about the photo-induced reaction dynamics. Then also his work on the dynamics of photo-induced fragmentation for open shell models and radicals, with unit for, in both things, with units of computing the ab initio mass spectra for distribution of products. Then Brandon Disroot, who hired to some company, I don't remember the name, he left the company, but his deeds are alive. With help of Dr. Han and some editing, his work is published online today's morning in molecular physics. So it is about carbon nanotubes exposed to aggressive chemical environment of the hydrogen peroxide that leads to formation of different groups, like functionalizing by hydroxyl, epoxy, and some other groups that affect the ability of this material to conduct electricity. And another work that by Dane Hogeboom. Today he's also on the process to be, he is graduated. He's not continuing to my knowledge to the graduate school, and he's on the process to be hired to 3M, and right now he has a temporary job that he likes. Ask me in private if you're interested. His work was resubmitted to Journal of Nanomedicine, and it got positive reviews, and it got resubmitted today, so hopefully it will be completed. So it is about spontaneous combustion of fuel and oxidizer. So this couple of slides, I'm sort of cheating. I was showing the same slides at the first group meeting in the fall semester, but at this time they all were in drafts and they didn't have the links to publications. So they were in processing. Now all of them are accepted. So for photophysics, there was a work by Dr. Jensen, Stephanie, who is a postdoc at North Carolina, Wake Forest University. And this is about nanowire. So we are looking not along but across the nanowire of titanium dioxide, getting the photoinduced charge transfer to surface doping. So doping of transition metal. And this work was done in the resolved spin polarized version, having some methodological novelties for processing dynamics in presence of when system is in open shell configuration, which is important when one has transition metal dopings. So there was a work by Sam Brown from Eric Hobby's group about photoluminescence of silver nanoclusters. So right now in this part of the group, no one continues this direction, but in Dr. Skill's group, Javed is pursuing this research further. So it is the small number of atom silver nanoclusters surrounded by DNA bases are found experimentally and by computation to be efficient emitters of light. And this method was following up the methodology with open shell speed resolved dynamics of electrons. And the main discovery was that most luminescent properties appear when the system is highly cationic. Like for this example, it was 5+, and for the current expert in the field, Javed, may find clusters with different oxidation numbers being luminescent. There is a very important work, although it is published not in the top journal, but just mid-range respected journal of molecular physics. It is by, well, if I give titles, it is by Dr. Han and Dr. Fogel. Let me see if he's smiling. So it is the next step. When one is, I just hold for a second. Since there are no undergraduates, I'm going too quick, but one of the main strengths and interest and activity in the group is to explore dynamics of photoexcited state, how the excited state changes in time. So it is not included in standard public or commercial pieces of software. Maybe in one day it will be included, but right now we have some suite of homegrown codes to do this. And as time goes by, this suite of code is being updated, improved, and developed. Originally, it was working only for closed shell systems. For example, if it is oxide with balanced number of metal and oxygen, one doesn't need spin polarized. Then the code was updated for spin polarization when there are independent properties of electrons with different quantum number of spin, alpha and beta. And next very critically important step is an update of the code for quantum dynamics for the situation when spin is not a good quantum number, when there is a heavy elements that include occupied orbitals with high orbital angular momentum, and in these situations the spin is not a good quantum number. So one cannot play and do something and get trustable results for a spin polarized model. There one uses so-called non-collinear spin. When there are superpositions of alpha and beta ground basis states of spin, and expectation value of spin can be aligned not only along quantization axis but any arbitrary direction. So this is the only basis that where one can deal with spin orbit coupling. So this is the first paper that treats quantum relaxation of excited state in presence of spin orbit coupling, and it was tested on the example of lanthanide doping, which is a next level of complexity compared to transition metal for praseodymium and cerium, right? In transparent host matrices. So it is, and additional thing that it was also accompanied by computation of photoluminescence, which is main application of these materials. So next thing that was completed is by Aaron, who explored the photo-induced charge transfer, and more specifically Hall transfer between cesium lead halide perovskite nanostructures and acceptor molecule, which was taken as a simplified version of most popular acceptor. Instead of big molecule of several hundred atoms, it was reduced to whatever, about 40 atoms molecule that holds similar electronic structure, work function, offset, ionization, and the main findings were that character of presence of bond plays critical role on the rate of charge transfer. It changes it by 3 orders of magnitude.
Mm-hmm.
And another thing that Aaron carefully processed the multi-exponential character of relaxation, which was left for the future in all other works. And most recent paper by Dr. Fogel, by John, is also on perovskites. So here it is bulk perovskite where a vacancy, a defect is introduced. And this defect was treated with taking into account all possible arsenal of methodologies: spin polarized, non-collinear, and dispersion of K-points. The dispersion of K-points is next challenge for our methodology development, because right now we are working in gamma point approximation, while for periodic solids it is not always acceptable. So if some of us work in the focus on the zero-dimensional quantum dots or molecules, then we can forget about dispersion. But as soon as we go to periodic materials, it is often non-negligible. And this is a substantial foot in the door to deal with radiative and non-radiative processes in presence of all of these effects. Okay, so here is an update how the research can or cannot be supported. So right now we can get support from, well, in this part of group for Javed and Levi, it is different story. So from departmental startup, now the shared with another group grant on the carbon nanotubes, but it is running for another few months. It will be done soon. And we do have recently awarded facility grant to use NERSC for several, well, I wouldn't say several, couple of million compute hours. And there are, how many? 8 active grants that, at least if some of them or one of them will come through, it will help us to continue active research. So what is really important? So there are local grants for photochemistry, one grant about polymerization of silanes, another for combustion. So it is based on work, ideas, and talent of Dr. Han. So and if there will be undergraduate researchers who are interested in this or maybe graduate researchers who are interested in this activity, it can be continued. And those two are not very prosperous in amount of finances, but they have highest chance for success. And there are several federal pending grants on the doped perovskites, on the carbon nanotubes, which is a collaborative continuation of previous one. Then the photochemistry, which is bound with these two, also substantially based on talent and ideas of Dr. Han. And there are 3 other grants. One, they are collaborative. One is on the surface chemistry, in collaboration with surface chemistry group at NDSU and UND. Some of us know some of the co-PIs on this grant. And another 2, metal organic complexes and data mining, which are rather broad, so one can connect them to any research if they come through. So the goal for our research activity is, the far-reaching goal is to continue development of electron dynamics research code development to the level that it will become universal. So we do have improvements towards spin orbit, and right now there are active work in to enable the dispersion of momentum. Some of the, from point of view of photochemistry, there are several minor approximations. I cannot name most leading of them. They are equally weighted, but removing them one by another, one can get more reliable and trustable code. But right now it is already good enough to apply to broad spectrum of photochemical processes and molecules. From more practical, cynical side, we will arrange our effort in form of preparing presentations for conference and then preparing the proceedings of this conference. I'm not telling that it is the only and only right way to do research, but it is a way to organize multi-person effort in a short time. So if we do, if everyone does approximately the same practical step at the same time scale, then it will optimize the effort. And right now there are several abstracts submitted to Sunnybell. The plan is that we will dedicate at least about three meetings before the conference to deliver drafts of the presentations on the group meeting and provide collective feedback. So I am aware of tentative titles of most of the abstracts, but I do not remember the name of the abstract by John. Maybe I have seen it, but I have forgotten. So please remind me or share the. And there are, I don't know how many, but there are several abstracts from Dr. Killian's group, and probably this part of our common group meeting activity, authors would also vote and elect to present their presentations and get feedback. So while setting up a schedule, you'll need titles, and if there are more than one or if there are more presenters, just to arrange our effort. Right now, I think it is still possible to go over the whole list during one meeting. So we can do like 2 or 3 iterations in 2 or 3 meetings. If it goes more than a dozen, then one needs to split, like half one day, half another day. What I failed to do in the last 20 minutes before the meeting, I didn't arrange them according to photochemistry or photophysics efforts. Right now they are more randomly oriented. next time if I repeat the slide, I will rearrange. So in this research effort, there's a new direction. There is a new direction not realized, or realized only in very small amount, only partially before. So I'm going to tell about tunneling and quantum vibrations, and John was doing it a couple of years ago for another system, and now we are looking on this process in application to different systems again. So quantum nature of vibrations could become the third thrust, third direction of research and intellectual activity. So recent, well, things that are not published, I'm not sure if they can be called discoveries, but from my view, it is a discovery. So recent results, recent discovery by Dr. Han it is not published, closed information, do not disclose. But there is a discovery that the rate of reaction depends drastically by orders of magnitude on whether quantum nature of nuclear vibrations is taken or not taken into account. And right now there is an addition to the suite of codes that takes it into account. We are going to take this idea and analyze and process it from different aspects and for different systems, including both photophysics and photochemistry. For photochemistry, it is just quantum nature of nuclear degrees of freedom. And for photophysics, it becomes critically important for excited states of soft systems, where the photoexcitation may induce bond elongation. In all activities for electron dynamics, we were approximating excited state potential energy surface equal to the ground state potential energy surface. Levi may object to this statement. Oh, he's not.
I think it's fine.
Okay, but he's involved in this approximation, so therefore he's not criticizing it. And for soft systems, for molecules deposited for organic and inorganic interfaces, and for dopings, transition metal dopings into crystal matrices, this effect may become substantial. This effect may become substantial in the following sense. Oh, this one is touch screen. Okay, then this is a really great room. I will just do a little. Okay, and I will write over. So before, all our activity was assuming that ground state and excited state have the same center and curvature of potential energy surface. But if we do have inhomogeneous impurities, the parabolas can be, or maybe it's more complicated surfaces, can change their curvature, and they can change their equilibrium position. And if this is a situation, then there will be quantum effects of so-called Frank-Condon factors, where the most efficient transition happens not on the resonance between optimized ground electronic structures, but between energies affected by nuclear reorganization, and also the intensity of radiative and at the same time of non-radiative transitions are also affected by change in these potential curves. So this effect is very interesting to check in application to die to semiconductor interface. And since we all are so busy, there is an undergraduate who will explore this opportunity in collaboration and under leadership of Aaron. And this is even more important for doping when transition metal doping is introduced into the semiconductor. So, this is a known effect for ruby laser, for sapphire lasers, and right now it could this effect could affect the efficiency of perovskites doped by transition metals. So this is also too much for a single person, and this seems to be a tandem research of mini team of graduate plus undergraduate. So I'm kind of done. So we will need to develop schedule or develop ideas about schedule for the next meeting. I plan to share the Google Docs document with just empty dates, and then each of us can put him or herself there or remove if someone else puts, and then we will do it self-growing system. There is in the Dr. Kilinas group, there was a tradition to assign one of the group members responsible for the schedule, and it will be our backup plan if self-growing schedule will not work. But let's try first self-growing schedule plan. Right now, I'm going to give the stage to Aaron, who will give a brief update on this nuclear reorganization thing that he was exploring based on his curiosity. Are there anything that I need to answer? Levi? John?
I'm good.
Okay.
No, I'm good.
Okay. Then let me invite Aaron. And please check if I uploaded the right version. You cannot blindly trust me in such things.
Looks like it.
Okay.
1/8. Yesterday was the 8th, right? Maybe?
Yes.
Okay, so yeah, that was the last time I updated it. So,
And if you want to, the camera is focused on screen only. If you stay here, we are not seeing you.
that might be a good thing for So, yeah, as Dimitri kind of preluded at the end of his talk, one of the things, or one of the pet projects I've been kind of wrestling with over the last couple of months with some collaborators is a manganese-doped perovskite quantum dot. So, if I knew I was presenting today, I would have put in a couple more pretty pictures, but this is just a page that I've been using to collect my data. So here on the left, you can kind of see this is the model of the perovskite quantum dot, and then if you look at it at a better angle, in the very center is the dopant, and it's surrounded by an octahedral ligand field of bromine atoms. So this is the bromine, and then there are 5 others. And so to get a rough idea of what the reorganization energy in the system is you need to make 2 parabolas for potential energy surfaces, you need 4 points. So here is just the ground state geometry optimization, spin polarized, and it's in a high spin configuration, because from previous work we found that's the the lowest energy that it takes is high spin. So then we have a ground state structure. Then we also do an excited state geometry optimization for the optical transition that occurs in the system, which is a spin flip from alpha to beta. So we do an excited, so it's basically just do a geometry optimization with n up down equals 3. That forces it to take the spin configuration that it would take for an optical transition. And then
Aaron, what's the total count of electrons?
a lot.
No. Is it even or odd?
Odd. Yeah, it's odd, I believe. 2809.
So what is the value of n up down if you do not constrain it? What is the difference between up number of alpha and beta electrons if you do not apply any constraint?
I think it normally takes the high spin configuration
But
without specifying an up down. Is that what you're getting at?
There is a thing that I do not understand, but I want to understand. Is an natural n up down integer or non-integer? Can we? Is it normal if we occasionally get half of electron of an orbital, or we need to do any effort to avoid it? Should we increase natural n up down by 1 or by 2? What is your instinct or experience?
So, well, it depends on the transition that occurs, I guess. So in this case, you have an optical transition occurring from the dopant to itself. And since it spin flips, so ground state has 5 electrons pointing up, so 5 up states. Then an optical transition, since they're all in the up state, it has to flip to get into the other orbital. So then these cancel and you're left with 3.
So you
spin up.
remove 1 up and add 1 down. Therefore, it changes by 2, from 5 to 3.
Yes.
Okay, makes sense.
Okay, so then oh, then so for the other 2 points I need on my parabola, you take your ground state geometry optimized structure, then you force it into the excited state. So you set n up down equal to 3, so it takes electronic configuration of that transition state, and that would be, which point would that be? So ground state is here, so that'd be this point here, and then you take the excited state geometry optimized and you force it to take the ground state electronic structure, so high spin configuration. That would be this point here. And so then with those 4 points, you can kind of curve fit to a parabola. This isn't exact, but it's a qualitative measure of the potential energy surface. And the weird thing is that this is the ground state. In the excited state, the bond actually contracts, so you get a shorter bond distance in the system.
Hey, Aaron,
Yep.
what's your internal coordinate?
Internal. Oh, so for this one, it's the manganese bromine 22 atom. So on this figure here, so this is
Oh,
what
okay.
I got as the coordinate for that one. So I thought that was kind of an interesting finding. So then I looked at all of the surrounding bond distances in the system. You can, and then I made a table of the ground state and then the transition, or the bond lengths in the excited state. You can kind of see that for 4 of them, there's a bond contraction, and then 2 of them it either elongates or it doesn't really change it at all. And then what I found just looking at the local environment of the dopant, you can kind of see that the 4 bonds that contract are kind of symmetric with each other around this axis here. So these are all the 4 bonds that contract. And then the one that elongates is this guy here, where it's like an asymmetric bond because it looks like that the dopant is bonding to only 5 of these ligands, and then this bromine here is kind of more attached to a lead that's hanging out over here. If you just think of general chemistry, you know, that manganese manganese 2+ has 5 valent electrons, so you'd think it would make 5 bonds. So that's kind of how I rationalize that it bonds to 5 of the bromines and then lets one of them kind of hang out by the lead. Then, yeah, I just thought it was interesting that you see bond contractions, because normally, like if you're dealing with a molecule, you'd expect that in the excited state the bond length to be longer. But so that means in a crystal there's a different dynamic going on. I don't know if it's a change in bond character, whether it's more in the excited state it changes to more covalent, so they become more closer to the dopant. I don't know, it's something I've been kind of wrestling with over the last day, trying to rationalize it, but yeah, that's what I found from looking at the nuclear reorganization for the optical transition in the system. And then, yeah, this is just a bunch of bad data that I had.
Okay, let's go to the good data.
Well, that was it. It was just 2 slides.
Okay, let's upload to Aaron. So any questions?
So what is the energy barrier from the 5 and 3 in the page number 2 from the graph? I mean, yeah, so if we go to the ES to the lowest GS,
This guy?
yeah.
So yeah,
So
this,
what is the energy barrier? I mean, how much if we consider the Marcus theory, if we want to cross the parabola, so what is the energy difference of the crossing and the ES? It seems like it's on very, very small energy.
well, this energy difference here is like 2 eV. So it's not the scale because I just made it in PowerPoint.
No,
But,
not that one. I mean that
Activation energy.
activation energy. Yeah.
So what Jabot is asking,
Oh, so it
If
excites
you-
up to here and then it,
No,
if you
If you're not
make a
correct.
little geometry and compute the height of this crossing point in comparison to this point, how does it compare to thermal energy or from temperature? Like if it is in 3+, would it spontaneously relax to the 5+, or it will stay there for infinitely long time?
it looks like it would. Like what's thermal energy in EV? It's like
0.03?
0.025.
0.03. So it looks like it would relax spontaneously.
Okay.
So it's
Say-
going to
assuming I-
spontaneously to 3, spin 3 state.
Yes.
So what is your research plan for, where would you go from here? Will you try n up down equals 1? Or since these calculations are not super quick, it is reasonable to think twice before running your job. So what is your twice thinking?
I don't know. I've been thinking about that, and I didn't really have any answer before either.
Okay. So right now your potential energy surfaces have different curvature. And if we run quantum dynamics with these surfaces, different curvature leads to quicker accumulation of error. Having same curvatures is a big sin, but numerically it is much more stable. Can you develop a justification how much of truth we will lose if we assume that excited state parabola has the same curvature as ground state parabola?
Well, I don't know. I guess I would actually plot it correctly first, because I think that that image is kind of misleading. Just the difference in the curvature. Because since it's not roughly like exactly to scale, I'm not sure what the coefficient is for the square term. So I don't know how much they're actually vary between the two.
Okay. What is your opinion? Oh, sorry. Anyone has questions? If not, I will keep asking. But you please develop more questions. What is your opinion?
Aaron,
Yep.
is this going to go into any MD, like non-adiabatic excited state molecular dynamics, or is this just pure single point calculation?
This stuff here is just single points. Like once
Is
you
it
get the
leading
geometry-
into dynamics? What was that? Sorry.
I was just saying, like all of these, like once you get the geometry optimization, it's single point. But then from I don't know. It'd be a lot of extra computation to do dynamics for the excited state.
Okay.
I think it's just correcting first, like the most prominent electronic transition that we're looking at. In this case, this would be the photoluminescence that comes from the dopant. That's why I'm looking at this.
But-
shape specifically.
Couldn't you have a lot of non-radiative relaxation since you have a crossing in your excited states?
Well, I guess, yeah, but I guess the most prominent electronic transition would be the photoluminescence from the dopant, so it would just be correcting that rate. I don't know if that makes sense.
Where would it thermalize to upon relaxation from any excited state except this one? Just because if you go on your two minima, how do you get emission?
Levi is telling that relaxation or recombination from this excited state to this ground state will be dark. So it will be not optical, but only non-radiative. In order
Because
to have non-zero Frank-Condon favorable Frank-Condon factors, the minimum of the excited state should be closer to more above of the ground state on the other side of parabola.
Yes.
Sorry to bug out so early, but I have another meeting I got to get to. Nice presentation, Aaron. See you later.
Thanks, Levi.
Okay,
Good luck.
and Levi, before you are going, he's good. Okay.
Yeah, it's okay.
We will need, well, I'm not sure if you can change anything, but we need at least not much protest of attendees for this time, from 4 to 6 on Tuesday. I know that some of you have schedule conflicts. Maybe it is intermittent regime when some attendance can be from 4 to 5, another can be from 5 to 6. And then everyone has chance to present, but not everyone has chance to listen to everyone. But we can cover it by having the recordings and then distributing it. So watching it on the sofa at home. So more questions to Aaron.
Just one thing I'm confusing from here. I don't know, maybe it's because manganese 5 ampere electron configuration is more stable, right, than last year, right?
Yes. It's a question to
Yes, but in these calculations, how it seems like more stable? Is it plus 3 is more stable? 3
No.
ampere electron is more stable.
What?
Which one is a? Maybe I didn't get the graph one.
So this is the ground state. So this is the
5 plus.
5 plus.
5 plus.
Oh, okay.
5 plus is more stable.
Yeah.
Yeah, it looks different, right? Because normally you'd expect them to be backwards, but
What is your opinion about paper by Guy Yao?
well, he showed that
Yes.
for the transition
Mhm,
metals that he looked at, this was a trend that he came upon, that
Mhm.
the number of valence electrons that in the d orbitals corresponds to the number of, I think, or the coordination around it with the ligands.
So, according to his paper, what is the determining factor for the number of coordination bonds? To my memory, the transition metal doping may gain different coordination number depending on some parameters, like oxidation state or concentration of doping, and depending on the circumstances, depending on these parameters, the coordination number may change drastically by not only by 1 but by 2, by 3.
I
So-
guess.
How does it project to this research? Why manganese is so unhappy that it doesn't want to be octahedrally 6 coordinated?
I don't know, it has lower energy this way. That's a standard answer.
Or what should we do to the system to make it happy and to make it octahedrally coordinated?
Well, why would that necessarily make it happy, though? Why would that make it happy?
Well, maybe if you change the total number of electrons to some different oxidation state, maybe it will restore back to 6 coordinated.
I get that, but
Well,
it the general-
it's too expensive to compute. We need to develop hypothesis prior to any calculation. A reviewer would ask this question, for sure. Like, how do we rationalize this observation? The 5 plus gives 5 bonds is good. For the oral presentation, it is perfect. And for answering oral questions on the conference is super. But for written report to reviewer, it will not work.
Like it
Brother,
says,
this is not a 5 plus. This is a 5 unpaired electron, right? Is it 2
Well,
plus?
for Braden, there is see this structure like a little cube.
yes.
In the center, there is a manganese ion that is by symmetry should be on the equal distance from 6 bromine ions, but by some reason it loves 5 bromines and hates the bromine number 6. And the intuitive explanation by Aaron was that manganese has 5 unpaired electrons, therefore it creates 5 bonds.
Yeah, because this one here isn't bonded to here. So then if you,
Well, the difference is not drastic. It is not like by 10 angstrom. It is
it's
by 0.1 angstrom difference.
so it's manganese 5 plus. It's like 0.6,
Yes.
0.7.
Manganese 2 plus,
2
with 5, 2 plus with 5 unpaired
Oh,
electrons.
Oh. I don't know, maybe it's just because I'm not well versed in ligand field theory, but is it always assumed that the ligands are symmetric around the metal?
Yulen? It's not right. right now, I'm confident that Yulun is well versed in Wigan field theory, and maybe we take in organic this semester.
Took it last.
Okay, so
I think.
it could be any
I think no.
coordination, like pyramidal, tetragonal, square planar.
And all of those are idealized. You can have squishing of any one of those in Ligon field theory as well. So it can be off idealized.
So Wigan field theory just please correct me because I never took inorganic chemistry. So Wigan field theory establishes a correlation between symmetry and bond distances and splitting of d levels, but it doesn't tell which which configuration of those nuclei is the best. It's question to another theory. In optimization procedure is not included in Wigan field theory, to my understanding.
I agree. From what Dr. Rogers said.
Okay. Well, no. Huh? John disappeared. John,
I have to go meet someone right outside a second. I'll be back in a couple minutes.
Okay, that's fine. So no one of us has immediate answer, but it is just thing to keep thinking about.
Okay.
Yeah, it's pity that Austin is not here today, but I will make sure that he watches it in recording.
Okay.
Okay. More questions? If not, let's thank Aaron once again. So basically we are done. We'll just wait.
Theory on triangular bipyramidal.
We'll wait for John to say goodbye to him.
Bond distance increases. This kind of thing, right?
Say that one more
So
time.
how many weeks is
In the
before
triangular bipyramidal,
the
which is
Sanibel?
if the ligand attached on the
When is it? The
triangular
17th?
Yes.
the top and bottom,
Five?
the
Four?
bond is will
Four.
increase, right?
4? So basically we need to
The
assign
triangular
4
atoms shorter than
no, 3 meetings for preparation of Sanibel, and we have 1 for
And it also
another
depends
subject.
on the
So maybe
ligand.
all meetings before the Sanibel will be just going through
triangular bipyramidal.
presentations, and next time we will check if there will be some
But if you know
special activity. Okay,
I don't
Anything
know, that's might be.
I can. Oh, John is here. Aaron has already completed, but if you have questions to him, you still can ask.
Okay, well, I guess 2 quick questions. So one you were mentioning about, distribution, changing of bond hybridization. Have you looked at just the total charge density files and just plotted them on top of one another to see once if it relocalizes anywhere away from that doping atom?
I had that idea today, but I haven't pursued it yet.
Okay. And then my second question is, so you're talking about how to symmetrize the potentials or the excited state and the ground state, so at least they have the same type of shape. So if you do that, do you expect you would get any type of shifting, crossing one of the ground or the minimum energy points? Like, would you get into like an inverted region?
Inverted region. I don't have a clear picture in my
John, can you please quickly cover the concept of inverted region?
Well, okay. So if you think about your 2 potentials, the way they intersect. So if this is one 1 ground or minimum energy point. Normally it's something like this. Maybe it looks a little bit easier like this. I don't know. And so that you get a clear crossing, but as soon as you move one of the potentials and it moves back, oh, maybe you can't see that, it moves back across the minimum, now you have almost an instantaneous drop that would happen without a whole lot of potential reorganization.
I don't know, I think the changes in along the coordinate axis are big enough where that wouldn't happen.
Okay.
0.08 angstrom difference, so
Okay. Well, no, that could easily be. I just didn't know if yeah, you thought that might be something that comes up, but
I did before, so maybe I'll.
okay. Thank you. All right, no, that's good. Thank you.
John,
Yes.
the possible idea is that if one makes excitation between natural perovskite localized states, not the doping, but like from orbitals localized on iodine to lead, there will be not much reorganization of bonds involved into manganese, and it will be in inverted region as you explained. Make sense?
Yeah, no, that's good. Thank you.
Okay. Okay. So, please develop your wish list. Although we will not have much freedom in our wish list. Most of time will be invested in preparation for Sunnable, but if you want to do a journal club or report breaking news of your discoveries, we will need to set up a schedule so that we do not, some of us do not feel nervous of uncertain plan of the meetings. So the link for collective editing of Google Docs will be distributed so that you can put yourself into a time slot or remove yourself from there. Anything else we need to do today? Okay, if not, then the meeting is dismissed and we'll go off record, and I'll just stay here in case there are some one-to-one questions.